Hello everyone, I'm Zian. I'm presenting our work, Learning Indoor Inverse Rendering with 3D Spatially Varying Lighting. This is a joint work with Jonah, Sanya, and Yan. The image formation process involves the interaction of scene surfaces and light transport, and finally captured by camera sensors. In modern computer graphics, given the scene geometry, surface material, and lighting conditions, a graphics engine can simulate the process and render photorealistic images. One natural question is, can we reverse this rendering process and recover the scene properties? The task of inverse rendering can date back to 1978, proposed by Barrow and Tannenbaum. It aims to estimate scene geometry, surface reflectance, and lighting from a single image. This is a challenging ill-posed problem. We want to assign the correct contribution to each component based on only observed pixel values. These disentangled scene properties are important to many image editing applications. For example, we can insert virtual objects into a given 2D image and make it look realistic. This is useful in many AR applications. Before deep learning methods become popular, classic methods usually approach to optimization-based framework using priors of human knowledge to constrain this ill-posed inverse problem. One representative work is SURFs. It proposed a statistical inference framework and optimized for solutions that are more likely to happen. However, real-world scenes are complex. These methods usually rely on handcrafted priors that are too simple for real-world and can lead to severe artifacts. Also, the test time optimization makes this method hard to run in real time. Considering the limitation of classic optimization-based methods, recent works favor data-driven learning-based methods. The two recent state-of-the-art methods formulate the task as image-to-image translation and train with synthetic ground truth. The major challenge here is how to represent lighting. Neural inverse rendering by Singh Gupta et al. Use an environment map to represent lighting, which cannot handle spatially varying effects. As a remedy, they introduce a neural renderer to account for these effects. However, this neural rendering module is not interpretable and thus cannot use in downstream applications. Li et al. Predicts per pixel spherical Gaussians to represent 2D lighting distribution, but it still lacks 1 degree of freedom and sacrifices angular high frequency at each pixel location. We argue that indoor scenes contain complex 3D light transport and a 2D lighting representation is insufficient. In this paper, we propose a unified learning-based inverse rendering framework that formulates 3D spatially varying lighting. Given a single image as input, our model jointly estimates albedo, normals, depth, and the lighting representation. The lighting representation here should be able to handle 3D spatially varying lighting and high-frequency details. With 3D spatially varying lighting, we model the lighting variation within the scene and can realistically insert moving objects. With angular high-frequency details, we can make specular and transparent object insertion more realistic. Also, the lighting representation should be in high dynamic range, or HDR. Digital images usually quantize into the range between 0 and 255 and clip the saturated pixel values. However, a higher dynamic range is crucial for rendering effects such as cast shadows. The question is, how do we represent lighting? Lighting variation depends on both spatial location and viewing angle. The 5D function describing the incident lighting in every location xyz and viewing direction theta phi is also known as the light field. Directly modeling the 5D function is intractable. Inspired by the volume rendering techniques, we propose volumetric sphere Gaussian, a voxel-based representation, and use volume rendering to render the lighting distribution. Volumetric sphere Gaussian is a voxel-based representation for the full scene. Each voxel corresponds to a scene location in 3D. The voxel can be treated as a light source. Each voxel contains a set of sphere Gaussian parameters representing the excitant radiance. These parameters include the HDR intensity value C, emission direction mu, and the sigma to control the sharpness of a spherical lobe. When looking at the voxel in a viewing direction V, we can compute the outgoing radiance with the formula of sphere Gaussian. In addition, each voxel is also assigned an alpha value indicating opacity. The illumination at any spatial location and viewing angle can then be rendered by volume rendering. If we want to compute the radiance at position P and viewing angle L, we can shoot a ray and select equally spaced points along the ray. Then we use the alpha channel to composite the radiance along the ray. We now introduce the model architecture. Our monocular inverse rendering model jointly estimates albedo, normals, depth, and a volumetric sphere Gaussian lighting. The network architecture consists of 4 submodules and is a combination of 2D and 3D networks. First, we pass the input image into the direct prediction module, where we process the input image with a ResNet backbone. This module makes an initial prediction of the intrinsic images and extracts a feature vector encoding global lighting information. After that, we feed the input image, initial intrinsics prediction, and global lighting feature into the joint prediction module and jointly predict the lighting volume. In this module, we utilize features from 2 streams. In the top stream, we unproject the visible field of view information into a 3D volume and process it with 3D convnets. In the bottom stream, we decode the global feature vector extracted from input image into a feature volume. The 2 streams are fused together to predict the volumetric lighting. Then, to enable joint reasoning during inference, we use a differentiable re-rendering module to re-render the input image using the current intrinsic image prediction and lighting, and then we can subtract the input image and compute the error of the re-rendering. Also, since ground truth HDR light field is usually not available, this module will also serve as a valuable supervision signal. Finally, the joint reprediction module conditions on the current prediction and re-rendering error and jointly refines the initial predictions. Together, the 4 submodules build up for our full inverse rendering model. To train the model, we use a synthetic interior net dataset, which contains realistic renderings of panorama sequences for indoor scenes. For each input image, we have ground truth albedo, normals, and depth. We also have novel view panoramas and camera poses. These panoramas can indicate the lighting distribution at the corresponding camera center and can help supervise lighting prediction. Note that the panorama here is only LDR, so we can only use this information to supervise the LDR appearance of the lighting volume. With the input image, our model predicts intrinsic images and the lighting volume. For albedo, normals, and depth, we can directly enforce the consistency of the prediction and ground truth. For lighting supervision, with a novel view camera pose, we can query into the lighting volume and render a predicted novel view panorama. We enforce this rendered novel view to be consistent with ground truth and thus supervise the LDR part of the lighting volume. As we mentioned earlier, the dataset does not give any HDR information. Then how can we supervise the HDR part of the lighting? To address this, we use the differentiable rendering module to re-render the input image. We introduce the re-rendering loss, which encourages the re-rendered image to recover the input image. It enforces the model to learn physically correct lighting and recover HDR information. For example, if the network does not predict HDR components well, the re-rendered result will be darker than the ground truth, and this signal will be backpropagated to the network. To sum up, the loss for training comes from 2 parts. The direct supervision directly learn knowledge from synthetic data, and the re-rendering constraint enforce the model to learn physically correct predictions. This brings some interesting properties. For example, our model can learn HDR lighting components even without HDR ground truth, and it also encourages lighting variation within the scene, making the results more vivid. We refer to more training details in our paper. We now compare with prior works and validate the effectiveness of our method. In these tables, we evaluate albedo, normals, and depth on the synthetic interior net dataset and the real-world IIW and NYU dataset. Compared to prior methods trained on the same data sources, we got better performance on both synthetic and real data. In this figure, we show qualitative results of albedo, normals, and re-rendered images on real-world data. Our method can generate albedo and normals with less artifacts. To understand the behavior of different models, we visualize and compare the re-rendered images. The environment map predicted by NIR cannot handle spatially varying effects and only produce almost uniform re-rendering results. The neural renderer used in NIR can introduce spatially varying effects, but may easily generate artifacts and hurt the performance of other properties. Compared to prior works, despite handling the more challenging 3D spatially varying lighting, our model outperforms the baseline and can re-render complex lighting effects. We qualitatively compare the lighting prediction with state-of-the-art inverse rendering and lighting estimation methods. We visualize insertion result of the purely specular sphere, and on the bottom row displays the estimated environment map at the inserted location. Our method can both produce realistic cast shadows with HDR lighting prediction and preserve angular high-frequency details, outperforming all prior methods. In the video comparison, we can see the environment map predicted by NIR cannot handle spatially varying effects. Li et al. Suffers from spatial stability issues and cannot preserve high-frequency details. Lighthouse does not handle HDR and cannot produce realistic cast shadows. Also, it tends to predict uniform lighting intensity with less lighting variation. When training without the re-rendering loss, our model also shows similar effects as Lighthouse. This indicates the importance of the re-rendering constraints. Finally, we show more image editing results of inserting synthetic objects into real-world images. Our model generalizes well to real-world images and consistently produces realistic appearance and shadows. In conclusion, we proposed a holistic inverse rendering framework with 3D spatially varying lighting that efficiently disentangle complex lighting effects. Our method outperforms prior works and benefits downstream applications. Thank you for listening. Please refer to our paper for more details.